Welcome to today's YouTube tutorial on series and parallel connected sources and resistors. Today we are going to deep dive into the world of series and parallel circuit configurations, understanding how they behave and exploring the fundamental principles that govern their behavior. Understanding these concepts is essential because they form the foundation of designing and analyzing complex electrical circuits. Whether you're working with basic electronics, troubleshooting household wiring, or even building advanced systems, knowing how to handle series and parallel connections is an indispensable skill. So let us embark on this electrifying journey. So I will quickly give you an overview of what we'll cover in this tutorial. We'll cover series connections. We'll start by examining what happens when multiple components such as resistors or voltage sources, current sources are connected in series. We'll learn about the current flow, voltage distribution, and the overall resistance in a series circuit. We'll also discuss the real-world examples where series connections are used. Another point we'll cover here is the parallel connection. The parallel connections, and where this will see how current divides and voltage remains constant across components in a parallel circuit. In the former YouTube tutorial, I explained that elements that are connected in parallel to each other will have the same voltage, we have a constant voltage. So here we'll be noting, we'll be understanding how current divides and how voltage remains constant across components in a parallel circuit. We will analyze the equivalent resistance in parallel configurations, and we will understand why parallel connections are preferred. And the third one is when we now combine series and parallel together. When we combine series and parallel connections together, we'll look at circuits that feature both series and parallel connections. We'll learn how to simplify complex networks using the principles we've covered and see practical examples of these hybrid configurations. Throughout the tutorial, we'll use clear diagrams, simple explanations, and examples to make these concepts crystal clear. So whether you're a visual learner or you prefer a more theoretical approach, you get it covered. By the end of this tutorial, you will have a solid grasp of how to analyze and design circuits with series and parallel components. You'll be better equipped to tackle a wide range of electrical challenges and gain confidence to explore more advanced topics in electronics. So if you have any questions along the way, or if there's something specific you would like to learn more about, or there's something that you don't understand as I am teaching, feel free to drop a comment. I'm here to help. So without further problems, without further wasting of time, let's deep dive into the world of series and parallel connected sources and resistors. Let's go. Basically, we know what series and parallel combination is. Series are something that are connected side by side. So I have a component here, it's connected to another component, connected to another component, connected to another component. They are connected in series. So this is basic explanation of what a series connection means. But a parallel combination is when you are now connecting them in bridges. That is, you have a component here, right? It's connected with another component. It's connected with another component. We know what a parallel line means. Parallel lines are lines that have the same slope, right? They have the same slope, so which means that they can never meet. But in this case, they have the same slope, but it's not that they can never meet. They are meeting. The reason why we use the parallel is because they are having the same direction. When voltage is moving, they have the same voltage. So when we say we have the same slope, in this case we say that they have the same voltage. So they are not connected side by side, they are connected in bridges. Do you understand? So this is the difference, and this is how you see whether we have a series connection or we have a parallel connection. I know you understand what I mean by that. So to start with, I will go with the series and parallel connected sources. Connected sources. Where we have connected sources, that is sources that are connected whether in series or in parallel. So let's look at voltage sources connected in series. So I'll draw three voltage sources connected in series. So and basically you can only have voltage sources connected in series, right? There are the explanations to voltage sources connected in parallel doesn't make sense. Why? Because if voltage sources are connected in parallel, what do I say about components that are connected in parallel? They must have the same voltage. So if I have voltage sources connected in parallel, it doesn't make sense unless they are having the same voltage. If I say this is 6 volts and this is 9 volts, it doesn't obey the law of Kirchhoff's voltage law, because Kirchhoff's voltage law says that the sum of voltage in a closed path must be equal to 0. So if this is plus minus and this is also plus minus, this doesn't make sense because you'll be having 9 minus 6, which is 3. It's not equal to 0. So that's why you only have voltage sources connected in series and current sources connected in parallel. So those in those two configurations, that's when they obey Kirchhoff's voltage law and Kirchhoff's current law. And if you don't understand Kirchhoff's voltage law and Kirchhoff's current law, you can go to our previous tutorial and get a better explanation of what Kirchhoff's voltage law and Kirchhoff's current law mean and their applications in electrical circuits. So with this, we have plus here and minus here, plus minus voltage sources, and let me say this one is minus and plus. We have V3, V2 and V1. So if I want to combine these three sources, right, I want to get an equivalent source, what it will be. So what I do, it's just like I want to do a normal KVL, but this is not a closed loop this time, right? And let me say I'm going down, the current is going down, right? So when I'm entering V1, it will be V1 plus V1. When I'm entering V2, it will be plus V2. And when I'm entering V3, it will be minus, because the minus is the first terminal there, is the entering terminal, so minus V3. So the equivalent source for these three sources connected in series is what? V1 plus V2 minus V3. So let's now say V1 is equal to 6 volts, and this is 7 volts, and this is 5 volts. Sorry, and this is 8 volts. Let's say this is 7 volts, right? So what would that be? It will be V1 plus V2 minus V3, 17 volts, right? Which is equal to what? 6 plus V2 is what? 7 minus 17. So what would that be? That would be 13 minus 17, which is equal to minus 4 volts. What does that mean? It means that our minus will be up and our plus will be down, and we'll have what? 4 volts. Or if you don't want to draw it like this, we can say our plus will be up and our minus will be down, but it will be minus 4 volts. But it is more professional to draw it like this, which means that we are just switching the terminal. We'll say that we are just switching the terminal. Do you understand? Okay, so that is that about that. So let's talk about current sources in parallel. Current sources in parallel. So for current sources, it is only in parallel combination that they obey Kirchhoff current law. So aside in parallel it's because when two components are connected in series, same current goes through them. So if you have two current sources in series and they are not having same current, so it is not obeying Kirchhoff's current law, so it is violating Kirchhoff's current law, and that doesn't happen in electrical engineering. So the only configuration where we can combine current sources is when they are in parallel. That's when it obeys electrical laws. So let me say this is I1, and let me say this is going down, and we have I2, and I have I3 here, and it is going up, right? So my resultant current source is going up. My resultant current source is going up, right? So what would that be? To be I1 minus I2 plus I3. So basically what you need to check is what? The direction of the current. This is going up, this is going down, this is going up. Since I want my resultant source to be going up, so that will take the positive sign. So I1 minus I2 plus I3. Another way you can look at it is using the KCL, right? So I1 and I3 are going inside. That's why it is I1 plus I3. But I2 is going outside. That's minus I2. Do you understand? So that's how it doesn't disobey Kirchhoff's laws. Always remember, components in series, same current passes through them, and components in parallel, the same voltage are dropped in them. I hope you understand. So that is very, very simple to get. So let's do an example of a circuit with this. This is an example here, and we'll be using the idea of connected sources to simplify the circuit. So as you can see that we have current sources, we have voltage sources in series, right? So and therefore I can combine them. If they are not in series, you can't combine them, right? So let us do that. Let's just combine. So if I'm going clockwise, like this arrow, like the arrow I drew, so if I'm combining the source, and I want to have an upright source, that is plus minus, right? So I still have my 100 ohms here, then I still have the 220 ohms here. This 220 ohms, and this is 100 ohms. So if I combine this, what will I have? I will have minus 5. I'm going anti-clockwise, minus 3 minus 9. Minus 5 minus 3 minus 9. There's one volt here. There's 1 volt here, which is plus, so plus 1. So that's minus 16. So definitely we'll be putting 16 volts here. So when I'm still going anti-clockwise, I'll still read it as minus 16. So I've combined the sources. What is the next thing to do? Basically, we want to get what the value of I will be. So after combining the sources, what will I do? I'll use KVL, Kirchhoff's voltage law. And what would that be? That will be on the voltage on 100 is, let's say, is V100 plus V220 minus 16 equals 0. That's by KVL. So what is V100? V100 by Ohm's law, it is current times resistance. So what is that? 100 multiplied by I. The current moving through 100 ohm resistor is I. What is the voltage on 220? That's 220 multiplied by I. 220 I, and if you bring 16 to the other side, that will be 16. So if I add that together, we have 320 I is equals to 16, and therefore I will be equals to 0.05 amperes, which is what I can still write as 50 milliamperes. That is very, very straightforward. I hope you understand that. Okay, that's about connected sources and connected sources, voltage sources and connected current. It's very simple. When you have voltages in series, you combine them using KVL, and when you have current sources in parallel, you combine them using KCL, and that is straightforward. So the last topic here is the resistors in series and parallel. Resistors in series and parallel. So this is very, very straightforward. When we have resistors in series, you add them together. So we have resistors. I have R1, R2, and R3. So the total R is R1 plus R2 plus R3. So that is when I have resistors in series, I add them together. But when they are in parallel, that is, I have a resistor R1 here, another resistor, another resistor. Let me say R1, R2, and R3. So the total R is usually the reciprocal. So when we have resistors in parallel, we usually get the total R by using the reciprocals, the sum of the reciprocal of each of the resistance. R1 plus 1 over R2 plus 1 over R3. So, and that's it. So this is parallel. And this is when resistors are connected in series. So this is straightforward, and let us see an example in an electrical circuit. Okay, we use this question to explain the connected sources and also the resistance in series and resistance in parallel. One thing we would like to avoid is that we need to get the dependent source, the power and the voltage on the dependent source. Look at it. The voltage on the dependent source will be Vx. Why? Because all of them are connected in parallel. The current source, 6 ampere current source, 3 ohm resistor, 9 ohm resistor, and the 0.9 I3 dependent source, all of them are connected in parallel. Therefore the voltage Vx is the voltage you are looking for. And of course, for us to get Vs, we know that Vs will be equals to 0.9 I3, and that I3 is the current moving through the 3 ohm resistor. And therefore, whenever you are looking for a particular variable, make sure that you don't combine the components of the components with all other components. So I just use that to show you how to get the parallel combination of two resistors. So therefore we won't be combining this 3 ohm with 9 ohm, because we need this 3 ohm to get I3. Right, so let's combine this 15 ohm, 6 ohm and 6 ohm. Okay, 6 ohm and 6 ohm will give me 1 over RT to be equals to 1 over 6 plus 1 over 6, giving what? 2 over 6, which is same thing as 1 over 3. And therefore RT will be equals to what? 3 ohms. So the total combination of this is 3 ohms. And if it is in series with 15 ohms, and when I combine it together, it will give me what? 18 ohms. So the R equivalent is what? 15 plus 3, which is equals to 18 ohms, which is equals to 18 ohms. So that is simple. So and we can see that these two current sources are in parallel. So that brings us to the concept of what connected sources, and in this case they are current sources. So what will it be? 6 amperes, 4 amperes. That will be 6 minus 4, which is 2 amperes. So if I'm to draw my equivalent circuit, I'll be having 2 amperes on this side. So let me draw that. I'll be having 2 amperes here, plus going up 2 amperes. 2 amperes here, and of course I will be having the 3 ohm resistor. Then I will be having 3 ohm resistor in parallel to that. Then of course the 9 ohm resistor, and of course the dependent source, and lastly the 18 ohm we got. So we have 3 ohms, 9 ohms, 18 ohms, and we have the dependent current source here, which is 0.9 I3. And don't forget, this is the I3, and of course this is the voltage. So, and as you can see here, you can see that we can combine 9 and 18 because they are in parallel, right? We can combine 9 and 18, and when we combine 9 and 18, we have 1 over 9 plus 1 over 18, which will give us 18 into 2 plus 1. That's what, 3 over 18. So therefore 1 over RT, because to 3 over 18 is 1 over 6, which means that our RT is 6 ohms. So if I should redraw the circuit, I will be having 2 amperes here, then the 3 ohm resistor, um, then I have the 0.9103 and 0.91 I3, and of course the 6 ohm equivalent resistor. 0.9 I3. So, and of course the voltage on each of these is V. So how do you now get our V now? It's very straightforward. We can use the concept of Kirchhoff and Kirchhoff laws. So you can see that we have just 2 nodes here. These 2 nodes on top is just 1 node. The 2 nodes down too is just 1 node. So therefore we have 2 nodes. So at the upper node we can apply KCL at the top node. So applying KCL at the top node, what do we have? We have 2 is going inside, am I right? Then 0.9 I3 is also going inside. Then the current here is I3. and of course let's say the current here is I6, so it will be equals to what? I3 plus I6. And of course you remember that I6 is can be gotten using Ohm's law. The voltage on 6 ohm is V. The voltage on 6 ohm is V. So because the voltage on 6 ohm is V, I can say that it's the same thing as I3 plus V over 6. 2 plus 0.9 I3. Do you understand? So let us simplify that. Let us simplify that. So I3 minus 0.9 will be 0.1 I3. So what do I have? I will have 0.1 I3, right? And I will also have, remember that V can be gotten in terms of I3, right? The voltage on 3 ohms is V, and therefore we can say that V is equals to 3 multiplied by the current using Ohm's law. That's 3I3. So if I replace V by 3I3, I'll be having 2 plus 0.9 I3 is equals to I3 plus 3I3 over 6, right? Plus 3I3 over 6. So which will give, so in the next board, that will give me I3. This one is same thing as I3 plus 0.5 I3. So therefore I can say that this is 1.5 I3. 1.5 I3. So which means that I have 2 plus 0.9 I3 is equals to 1.5 I3. 2 plus 0.9 I3 is equals to 1.5 I3. So therefore I3 will be equals to what? 2 over 1.5 minus 0.9, which is equals to 2 over 0.6, and that will be giving me 10 over 3 amperes, right? Because if you divide both sides by 2, I have 1 over 0.3, and of course 0.3 is 3 over 10. 1 over 3 over 10 is 10 over 3 amperes. So I3 is equals to 10 over 3 ampere. The V that we are looking for is 3I3, right? Which is 3 multiplied by 10 over 3. That will be giving us 10 volts. So that's the voltage in the dependent source. And the last one, they said we should get the power, right? So power is what? Power is voltage times current, right? The power is voltage times current, and that is very very straightforward, as the current in the dependent source is 0.9 I3. So I have V multiplied by 0.9 I3, which will be what? 10 multiplied by 0.9 multiplied by 10 over 3, and the power will be given 30 watts, and that's straightforward. So the question we just solved explained how we can solve a circuit using KVL and KCL, using connected sources, using resistors in parallel and resistors in series, and we have applied all what we've learned to solve a particular question. So if you have any question on everything I've talked about, please drop a comment and I'll give you an answer. Thank you very much for joining this tutorial, and see you in the next tutorial.